Way back in Gen Chem 1, we learned about protons, neutrons, and electrons. And we learned how to look at a periodic table to be able to tell how many of each of these there were in an atom. And so, for example, boron, if I look at him, in fact, let's see if I can't do this on a chalkboard. If I look at boron, all right, what this symbol means, usually somewhere along the top is a number. Sometimes it's on the left, sometimes it's right, sometimes it's on the center. This is boron's atomic number. And this is his number of protons. And no other element only has 5 protons. Boron is the only one that has exactly 5 protons. And if I look back at the periodic table, this is arranged by atomic number. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. That's the atomic number. That's the number of protons. If I look down here, and again, this is usually at the bottom of that symbol, this is not the mass number. This is the atomic mass. And it is an average of all the isotopes. And not only an average, but it is a weighted average. Some isotopes of boron are much more common than others, and so all the various isotopes are weighted by their natural abundance, and that is the weighted average of all the isotopes of boron. Since it rounds to 11, it's very close to 11, it might be safe to assume that the most common mass number of boron is 11, and a mass number is a whole number because it represents the number of protons plus the number of neutrons. So if the mass number, if I'm looking at boron, which has a mass number of 11, now when we go to this symbol, the position of the mass number and the atomic number are flipped. Don't ask me why, it just is. It is common to see the symbol for boron like this with the 11 in the upper left-hand corner, which stands for the mass number, the 5 in the bottom left corner, which stands for the atomic number, which means this boron has 5 protons because he's boron. That is his unique atomic number. And since his mass number is 11, and that is the protons plus the neutrons, he must have 6 neutrons. 6 plus 5 is 11. So I can tell if I see the symbol, if I see a symbol in this format, I can tell how many protons and neutrons there are. We also learned about electrons. Electrons are very important for chemical reactions, as we've been seeing in the last several modules, the electrochemistry module especially, the acid-base module. Those charges in the upper right-hand corner tell you how many electrons there are. We're not worried about electrons as we move into nuclear chemistry. As we move into nuclear chemistry, we're only concerned with what is happening, can't talk it right, in the nucleus, and that's the protons and the neutrons. So having said that, now as I look at any of these symbols then, I can tell protons, that's the atomic number, that's how many protons. I can't tell mass number from the periodic table because it could vary. The mass number, there might be several different mass numbers for a particular atom, which are the different isotopes. But if I see the symbol written in this fashion, I know what the mass number is because it's listed right there in the upper left. In a nuclear chemistry reaction, we are concerned with which isotope we're talking about. We never were with chemical reactions. We never wrote numbers. After we did this module in Gen Chem 1, which is usually module 1 or 2, very early on, we never talked about it again because it wasn't important for chemical reactions, but it is important for nuclear reactions. So here's an example of a nuclear reaction. In this nuclear reaction, it's written in this fashion. Well, here, let's go ahead and start with it. I see thorium 234. That means that is the isotope of thorium, which has a mass number of 234. I would want to complete this symbolism by finding out the atomic number of thorium. So I'm going to come up here to the periodic table, and sometimes you have trouble finding symbols of things that, especially things that you haven't used much before. A little trick is this is his mass number. It should be in the ballpark of his atomic mass. It won't be identical to the atomic mass necessarily, but it'll be in the ballpark. So we're building a nuclear reaction. So that's his mass number. So I come up to the periodic table and I start looking at these bottom numbers until I'm close to 234. And there he is. There's thorium. And his atomic number is 90. So you may have to do a little searching, or you can Google it. What's the atomic number of TH? All right. So thorium's atomic number is 90, and that means a 90 goes in the lower left. This guy is undergoing a nuclear reaction with this symbol. This symbol is a beta particle. It must be, it must be memorized, but of course we don't have to memorize it. We can just put it on a piece of paper so that we can see it during the quiz. This will not be on the exam. The final exam does not contain any nuclear chemistry. But this is a beta particle, and a beta particle has a mass number of 0 and atomic number of -1, because a beta particle is essentially an electron. It was called a beta particle before scientists realized it was just an electron. It was discovered during nuclear reactions. It had certain characteristics. They could figure out the mass was 0, the charge was -1. They did a few more experiments. Yep, it's an electron, but we're already calling it a beta particle. Let's call it a beta particle. Sometimes you see it as beta, sometimes you see it as that E symbol, the electron. So I've got a beta particle reacting with it, and there that completes the numbers for beta particle. And I'm trying to figure out what is produced. This is my unknown. And it's also throwing off a neutron. Now, an N, it's a lowercase n, stands for a neutron. This is indeed the neutron particle that is found in all atoms' nuclei except for hydrogen. The most common isotope of hydrogen doesn't have a neutron. And a neutron has a mass of 1. If you may recall from Gen Chem 1 that the mass of the neutron is approximately equal to the mass of a proton, and they're both 1 atomic unit, but it doesn't have a charge. It's not a proton, so it's a 0 down there. So 1 and 0. Now to figure out what X is, what this unknown particle is, we balance this nuclear reaction, but we don't need thorium on both sides. We don't need beta particles on both sides. We need the protons and the neutrons to balance. That's the difference between nuclear reactions and chemical reactions. We need the protons and the neutrons to balance. That can be achieved very easily, mathematically, by looking at these numbers on the bottom. We'll add up all the protons on the left. It's got to equal all the protons on the right. So on the left, I have a 90 and a -1, and I do count that as a -1. So the left bottom number is 89. All right. All right. That means on the right, the number must also equal 89. Since I have a 0 for the neutron, that means this guy must be 89. Now what we're doing is we are balancing this nuclear reaction. We're making sure that it's balanced, or we're balancing it to figure out what X is. So I know that X has an atomic number, because that's what goes in the bottom left, of 89. Now, I now know what element it is. I could go look now. We'll look in a minute. I could know whether it's thorium, or I think that's, I don't know the names of some of these top big ones. That's actinium maybe. I don't know what that one is. It's Pa or Ac or another thorium, but you'll notice there's 2 options for thorium that have different mass numbers. I need to know the mass number to answer the question. So in order to do that, I will balance the top numbers. 234 plus 0 is 234. The reason I'm doing that is the top, remember the top includes both protons and neutrons. So if the protons match, then the protons and the neutrons must also match. We're balancing protons, we're balancing neutrons. You don't have to balance neutrons individually, you can just balance mass numbers and that achieves the same result. This also must equal 234, but you'll notice I already have a 1, so 1 plus what gives me 234. Well, this must be 233. And so now I know my right answer. It is whatever has an atomic number of 89 with an isotopic number with a mass number of 233. I've got a couple 233 options, so let's go see what 89 is. On the periodic table, 89 is actinium. I was probably almost right. So the correct answer for X is actinium 233. Where'd it go? Right there. So this is how you balance a nuclear reaction. And there are several of these particles, we're not done yet, that we have to learn, i.e. put on your piece of paper and have it handy for the quiz, put it on your notes. We have to learn these in order to be able to complete them. So let's do another one together. Are you guys filling this in as we go along? All right, you're welcome to fill in these answers. All of these are multiple choice. You're welcome to fill these in as we go along. Now we've got one that's a little bit more complicated. There's our X. And now we've got another symbol. Let me go back to the blue. We've got a P. A lowercase p is a proton, just like the proton we find in the nucleus, which has an atomic mass of 1, a mass number of 1, a mass number of 1, and an atomic number of 1. So a proton looks like this. We see our buddy the neutron again, which we saw up there. And then we have this new symbol. This is an alpha particle. And an alpha looks like this. On your screen, it may look a little different than on my screen, just depending on the font substitution. It's kind of like a proportional sign, but it's a little shorter. That's the alpha particle. This is the alpha particle. When scientists studied the alpha particle, they knew its mass, they knew its charge, they knew what numbers to put. It is a 4 and a 2. As they studied it, and as they studied it further, they discovered that it was simply a helium nucleus, no electrons, with the 4 and 2. If you go up, helium's atomic number is 2. The most common isotope is 4. It is simply a helium nucleus without its electrons. It does have a +2 charge, but this doesn't matter. We do not have to worry about charges. Although sometimes it is written, we don't have to worry about charges in nuclear reactions. So there's two more particles that you have to memorize or else keep on a piece of paper in front of you. All right, so let's do this one. Here we go. 234 thorium. Let me write it out here so I've got a little bit more room. Plus a proton 1 and 1 gives me an X. This is what I'm trying to find. Plus 3 neutrons. Neutrons are 0, other way, 1 and 0, plus an alpha, which is 4 and 2. You do have to worry about coefficients. Coefficients act just like they do in chemical reactions. That means I have 3 neutrons. So we saw thorium up above, otherwise we'd go look him up. He is 90. All right, we saw him up here, so he's 90. Otherwise, we'd have to go look him up. And then to balance it, on the left, I have 91. That means on the right, I need to have 91. 91. So whatever is with X plus 3 times 0 for my neutrons, which is still 0, I don't have to write it, plus another 2 for my alpha particle must all add together to be 91. So this guy, let me change color, this guy must be 89. All right. I'll balance my top. I got 235 on top, 234 plus 1. So over here, I have whatever X is, plus 3 times 1 for my neutron, plus my 4 for my alpha, must all add together to give me 235. So what is that? 235 minus 4 is 231, minus another 3 is that 228? Don't be afraid to use your calculator. Yep, 228. So it's X 89, 228. All right. Now we saw 89 again. We're not getting very much practice looking these up. That's okay. You don't need a whole lot of practice. All right. We saw 89 above, otherwise we'd have to go look it up. It's actinium 228. So scroll down till you see him. There he is. What do you think so far? Easy peasy? Cool. You may still be questioning why we're doing this. That's in the reading and the videos. If you want a big background, I'm trying not to complicate matters too much. This is how you balance nuclear reactions. Nuclear reactions happen totally differently than chemistry reactions, chemical reactions. Let's do one more together. I think we've got one more. Yep. All right. So what is X? Again, I kind of clarified because it might be hard to tell. I've got a beryllium 9 plus an alpha. Remember that was 4 and 2. Going to X plus a neutron. Remember the neutron is 1 and 0. Let's go look up beryllium to see what number goes on bottom. All the way up here. He's 9 is his atomic number, or I'm sorry, his 9 is his mass number, so I'm looking for masses around 9, and there he is. His atomic number is 4. All right. Oops, there he is. And here we go. 4 plus 2 is 6. That means I need a 6 on this side, so this guy's a 6. I already know what element he is. I could go look him up to see what atom he was. Then 9 plus 4 is 13. I've already got a 1, so how about a 12? So 12 and 6. Let me go look up who 6 is. And 6 is carbon. So that's carbon 12. All right, carbon 12. Piece of cake. All right, there's another way I can ask this question. Yep, we got 2 practices of these. All right. There's another way I can ask this question because this is the way nuclear reactions sometimes happen. They sometimes happen in a chain reaction, where there are successive nuclear reactions. So something reacts, undergoes a nuclear reaction, and whatever it produces undergoes a nuclear reaction, and whatever that produces undergoes a nuclear reaction, and so on. And typically there is an end point once you produce something that's not nuclear, not radioactive anymore. So in this question, I've got lead-210, and it undergoes successive beta, beta, and alpha emissions. That's 3 reactions. It emits emissions, it emits, it gives off a beta particle. So this lead-210 gives off a beta particle and produces something. Then this something gives off another beta particle to produce something new, and this something new gives off an alpha particle, beta, beta, alpha, to produce our final product. And it wants to know what's that final product. So I work out 3 nuclear reactions. So I go up and I look up lead-210. and lead is right here, over here somewhere. There he is. Lead is 82 for his atomic number. All right. So lead 82. Now I'm going to have to fill in the numbers for the rest of these, and I've got them on my handy dandy cheat sheet. So then as I balance this, it looks like let's get another color. All right, it looks like this guy also needs a 210 plus 0 is 210. Remember, this is a -1, so this needs to be an 83. Make sure that makes sense. 82 on the left, 82 on the right. That's what I'm going for. And 83 minus 1 is 82. Does that make sense? Now I could go look up what 83 is and get the symbol for him, but I don't have to because I'm not interested in what X is. I'm interested in what Z is. And as long as I know the numbers for X, I can do the next step. 210 and 83 undergoes another emission to give off a Y. So again, do your additions on both sides, 210 on the left. That means I have a 210 on the right. 83 on the left, this is a -1. That means this guy needs to be 84. I could go look up what 84 is, but I don't have to because I'm not interested in identifying Y. I'm only interested in identifying Z. So 84, 210. Now he's giving off an alpha particle. An alpha particle is a 4 and a 2 because I've looked it up. A little bit more complicated math, but not too bad. Let me do the bottom first because that's easy. Now I'm at an 82 on the bottom. And 210 minus 4 is 206. Make sure my math is right. Now I could go look up at 82, but we saw him right up here. That means Z is equal to lead 82, 206. There we go. So as I work through this problem, it's just 3 successive nuclear reactions to get that final product. And I don't have to worry about the ones in between because I'm not trying to identify them in this problem. Let me go up and grab my list of particles and bring it down here. Where'd it go? There it is. All right. Okay. We've got one more to practice with, and I want to point out that there's a slightly shorter way to work this question. Since we don't really care what X is or what Y is, we can just write one reaction for overall what's happening because that's how we get to Z. This is kind of like a Hess's law problem. If we add up these 3 reactions, we get the overall reaction, or mechanism steps. If we add up all the steps in the mechanism, we get the overall reaction. So in question 5, let's work this problem as an overall reaction. It's the same type of question, different emissions. These are emissions again. All right. This one is giving off a beta and alpha, a positron. This is a new particle. So let's add our new particles. A beta with a plus symbol. It has to have the plus symbol. Is called a positron. It's actually a positive electron, and it has a 0 and a +1 for its numbers. And gamma, positron and gamma are the new ones. Now this gamma looks like a V, but it's actually like that. And again, depending on the font substitution in your computer, you may see it a little bit different. And that's why I labeled it as gamma. A gamma particle is pure energy. This is something that electromagnetic radiation gives off, and it is 0 and 0. We still write it in the reaction, but it doesn't affect the balancing. So this is the complete set of particles you might run into for this module and the numbers that go with them, because you do need the numbers to be able to balance. So we've got I-31 and there are 1, 2, 3, 4, 5 emissions. So we would be stuck writing out 5 different reactions, but you don't have to. Write it as one reaction. So here we go. I-31, 131 undergoes. He gives off a beta, an alpha, a positron. That's just 4, isn't it? And a gamma. And produces our final product X. And X is what we're interested in here. Let me write that as one reaction. He's actually doing it a step at a time, but then whatever he produces is going on and doing the next one, so I can just combine those reactions. So let's write our numbers. So this is a 0 and a -1, 4 and a 2, 0 and a +1, 0 and a 0, and the X is what I'm trying to find. We'll need to go up to the periodic table and look up iodine and figure out what his atomic number is. So I'm going to scroll on up. I'll come back. I find my iodine. There he is. He's atomic number 53. So as I come back down here to this problem, he gets a 53. So the bottom is 53. That means this bottom must add to 53. Let's see what I got. I got a -1. Remember, if there were any coefficients, if you gave off 2 beta particles, there'd be 2 -1s. All right, so a -1. I've got a 2 already. I've got another +1. I've got a 0 and whatever X is. So do the little math. Again, don't hesitate to use your calculator. Is that 51? I think that's 51. Let's see if I make X 51, 52, 53, 54, 53. Yep, X is 51. So I know what symbol he is. We'll go look him up in a second. And on top, I got a 131. So I add all of those. Let me grab this. Move it down just a little bit so I got room to write. Let's see. So I got to add to 131. I get a 0. I get a 4. I got another 0 and another 0 and whatever my X is. So 131 minus 4. I did it wrong. I know, it's simple math. It's 127. So X is 51, 127. Let me go look up 51. I can already see I got a couple of 127s showing, 3 127s. Let me figure out what 51 is. So I'm going to scroll back up to my periodic table. And 51 is antimony, SB. So I'm looking for SB 127. So that's the basis for balancing nuclear reactions. This is a way to see the fact that in a nuclear reaction, it acts very differently than chemical reactions. We actually do change one element into the other. It gives off lots of energy typically compared to what regular reactions run. You'll see all of that in the videos if you want more of a background of nuclear reactions. But our task today is just learning to balance them first. We've got a little bit more to go. All right, everybody doing okay? Everybody feel comfortable balancing nuclear reactions? Give me a thumbs up if you do. I know you may have to switch screens. All right, I see one. There's a couple. Okay, good, good, good. It's not difficult. Again, it's you gotta look up a few things. You gotta look up your You got to look up, keep that list handy. And you got to do simple math. All right. For the last couple questions, and it is just the last couple questions, you will be pleased to know that you've already learned how to do these. These are kinetics. We mentioned in the kinetics module that one of the things about a first order reaction is that the half-life was constant, and we could use that to predict how much would be left after a certain amount of time because the half-life doesn't change as long as you're at constant temperature. All nuclear reactions undergo first order kinetics. So this is why we commonly use that term half-life with regard to nuclear reactions. It's important to know how long is this radioactive material going to last? What's its half-life? And the half-life is just how long it will take until half of it is gone. It's not radioactive yet, but you only have half of what you started with. So the series of questions we see here are just our same old kinetics equations that we saw a minute ago, literally, in the kinetics module, but applied specifically to nuclear reactions. Typically, we do talk about percentages here. We saw one problem with a percentage in the previous module just to kind of show you it exists. So here we go. If a tree dies in the forest, does anybody hear it scream, right? All right, and lies undisturbed for 18,400 years. What percentage of carbon-14 remains? Carbon-14 is an isotope of carbon that is radioactive. And as you probably know, all living things have a fairly large percentage of carbon in their bodies. I do, you do, plants do, anything, animals do, anything that's living has its basis in carbon. And a small percentage of the carbon is carbon-14. But with such massive amounts of carbon in your body, you've got a good bit of carbon-14 in your body. And carbon-14 is radioactive. That means you have radioactive material in your body as we speak. So do I. I'm probably a bit more radioactive than you because I've had lots of doses this year. All right. So you've got a lot of carbon-14 in your body. A tree has a lot of carbon-14 in our body. As we live, we consume food, we breathe air, we drink liquids, all of that, not water, but all of that that we're bringing into our body, the air we breathe has carbon in it in the form of carbon dioxide. Most of the food we eat was once living and has carbon in it. So we're consuming more and more carbon to replace the carbon in our body. So as the carbon-14 decays, it's being replaced. And so at any given moment, by body mass, we have about the same percentage of carbon-14 in our bodies. Once we die, we are no longer replacing our carbon-14. So once we die, the clock starts ticking on that carbon-14 that is radioactively decaying. And it continues to decay with a half-life of 5,730 years, and in 5,000, my remains, my pile of dust in 5,730 years will still be radioactive, and it will have approximately half the amount of carbon-14 that I had as a living being, as long as it's not been disturbed. If it blows in the dust, you can't gather it and measure it, that sort of thing. But if we see old living things, we find preserved bodies and such, we can measure the radioactivity in that dead thing and estimate how long it's been dead based on its radioactivity. And that's the basis for carbon dating, radioactive carbon dating. This is how that works. So if we find a tree that has died in the forest 18,400 years ago, it will have a certain percentage of carbon-14 remaining today based on the half-life of carbon-14, and we can calculate that using that half-life. You may recall that the rate constant is equal to the log of 2 over T1/2, and we can use that to calculate the rate constant for carbon-14. This will be in years, but it looks like all my time is in years. And I'm not going to round this. All right. That's the rate constant for the carbon-14 radioactive decay. And by the way, if you've got another problem with carbon-14, that's still the rate constant because as long as it's listing the half-life as 5,730 years. That's of course rounded to 3 significant figures. You might see a table with it with more significant figures, in which case you could recalculate the K. We also know that the equation, let's see if I'm just going to come up with one of the equations that we've seen. The equation for a first order process, the integrated expression for a first order process, in order to allow us to calculate what percentage remains is this one. And I know I need that because the time is equal to 18,400 years. I want to know what percentage remains, so my initial amount is 100%. We talked about this trick in the last module. The amount at time t, that's the percentage I'm going for. And then I just calculated the K from the half-life. So I know the T, I know the K, I know the initial amount. I'm trying to find the amount at time t. All I got to do is plug and chug, just like in last module. So let me plug in. Again, I'm going to use this unrounded value on my calculator. There's my K. It's 18,400 years. Don't go grab the half-life for this equation. Grab the time that the reaction is running. Again, I'm saying 100% initially. What's the percentage at the end? So let me plug this in. I am getting that the natural log of the amount at time t is 2.379 ... I'm not rounding it. Then I'm going to take the inverse log of both sides. And I'll get the amount at time t is 10.797. And that is a percentage because my initial amount was in percentage. It's the same units as your initial amount. So that's the percent that remains after 5,700, after 18,400 years. And that's measurable. So if we find a tree in the forest that has 10% of his carbon-14 remaining, he's probably been laying there about 18,400 years. Right, and this is how scientists do the carbon dating. Now, there are some estimations going on here. There's some rounding. This assumes a constant temperature, which is not exactly correct, but it gives us in the ballpark. All right, so these should look very familiar. Let's do another one. Strontium is also has a half-life. It's radioactive, strontium-90. Strontium-90 is, the half-life is 28 years. And the question is, how long will it take, so I'm looking for T, for a sample of strontium-90 to be 85% decomposed? And I'm just reminding you, if 85% is decomposed, that means 15% is remaining. I'm not going to use the brackets because usually we're talking about mass. So my initial amount is 100%. The amount at time t would be 15%. What is t? I need these and the K to do the first order integrated rate equation. I get the K from the half-life. And I don't want to round that. Do not round in the middle. On a plug your answer in, you might get the wrong answer. Might only get partial credit. On a multiple choice, you can be a little sloppy. So there's my K value. I'm going to grab the equation for first order. I said I was going to drop the brackets. That looks a little easier to solve for, which is I'm going for? T. I'm going for T. And so T equals log of A0 over AT divided by K. So the natural log of 100 over 15 divided by that answer I just got, unrounded. I am getting 76.635. I'm in years, so that answer is in years. That means in about 76.6 years, a little over 76.5 years, there will still be 15% of that strontium-90 left and radioactive.